Okay. Oh, sorry. Hello, hello. I know we're sorry. Okay. Oh, hello, hello. All right. I'm sorry. I know we're starting very late now, later even than I was in another meeting. It did go over. Hello. Thank you. Sorry. And I'm trying to make this fat. I do appreciate the hello, hello. But it is late. I do, but good afternoon. Yes. Thank you. Okay. Hi. Okay. Cool. All right. We'll do that. Yes. Let's do that. Okay. Yes. Hello, Rachel. Thank you. Good afternoon, Isabella. Thank you. Hi, Amanda. Thank you. Hello, Aaliyah. Good afternoon, Ingrid. I totally do appreciate it. Is that someone else? I really do. I don't want to waste anybody. Well, this is not a no. I love the hellos. I really that's a whole other subject. But so thank you. Okay, but it is a little bit late. My bad. And for the last couple of days, if you handed in anything, I haven't turned it back to you yet, and I apologize. I will get caught up. Uh, I want to make tracks because yes, so we're talking about this midterm exam. The midterm exam will be posted in a couple of days. You'll have plenty of time to do it. So the routine. Um, I will be posting updated. Oh, more people. Sorry. What I have not done yet, there's corrections that I discussed and put into the solutions to the midterm, and I will repost the updated, corrected version, and also the solutions to the midterm. They might have had some portion of solution for problem three, but they certainly didn't have a full solution. So my main goal for today, and we do have a little bit limited time now. My main, of course, if you have any questions, I want to try to answer them, and you can put them in the chat and stuff like that. And the more concrete, the more specific, the better. But my biggest agenda item really is to try to talk you through problem number three, because it's certainly the most intimidating, or it would be to me, and seems the most like out there, and it is. But that's why I want to talk through today, so that if you then you'll do the same thing on your real exam. And again, your real exam when it's posted will be certainly no longer or harder or weirder than this practice document. It might be a pared down version, like at the last minute, I might take things out and make it shorter, but it won't be longer. But anyway, I do want to so I apologize. I'm going to be a little spazzy today, but I want to give you a solution and explanation for the third problem. I want to talk to you about that. And again, all this will be posted while you're studying stuff. Like I will post a clean compiled version of the three solutions. But it'd be best to follow along here now. Okay, so I'm going to the third problem of the midterm. The screen is shared here, I think. And it begins by telling you a bunch of stuff. It begins by telling you a bunch of stuff that it doesn't even seem related to whatever we've been doing in class. And I know that, and that's like why it seems that way, and that's why it's an exam problem. But that's why we do exams this way with the practice and all that. But what's going on here is it's technically reminding us or declaring to us some other force, like not the spring force, not even the surface Earth gravitational force, or not the tension force in a pendulum, but it's introducing another force that can come along and accelerate objects. And this is called the gravitational force. Of course, we've been using it for 2 semesters. Person's here. Sorry. Okay. This is now, this problem three, excuse me, right, is now remind, reminding us that of the many, many forces that can ever combine on a given object to produce F net and thereby produce MA, right? One of which is a spring force, one of which might be the tension in a pendulum spring. Here's a force we're saying is the force of gravity, only we're actually expanding our understanding of gravity. And some of you might know this from physics one or from high school, and some of you might not, and it's okay either way. We're saying actually when gravity acts farther away, when gravity is at the surface of the earth, we call it mg, and we say gravity is always pulling everything in a manner that leads everything to fall at the same rate of acceleration, g, right? And the way we experience it for the last semester and a half is like, okay, earth seems to have this special like forces are pushes and pulls. Forces are, well, just that, pushes and pulls, interactions between objects. Other than gravity, up until now in this course, other than gravity, every force we've ever looked at, tension in a string, elasticity in a spring, normal force from a wall or from a hand, friction force from a surface, like every force we ever looked at up until now was always a push or a pull, an interaction between two objects, and always involved physical contact, touching between the two objects, except for gravity, right? Like gravity has the same effect as all other forces. It contributes to acceleration. But gravity seems to have this one property that all the other forces didn't have, which is that gravity seems to happen without material contact. It seems up until now at this point in physics 2, like up through physics 1, gravity seems to be this special ability that planet Earth especially has to pull all objects towards its center, toward the center of Earth. That's how we've been treating it. And we're saying there's always this force of mg that pulls you down to the center of the Earth. It seems to be a force that's dependent on how heavy you are. And that's all it seems to be dependent on, like not how far away you are or anything. We're not just how heavy you are, and the heavier you are, the more you're pulled toward the center of the Earth. So one might raise the question, why does the Earth have this special property that allows it to pull everything toward it without physical contact? And the answer is, well, the response is to ask why the Earth has this special property called gravity. It turns out to be kind of like asking, maybe I should write this. Well, turns out to be like asking, why does the Earth have this special property of sitting still at the center of the whole universe while everything revolves around it? Which is a question we all used to ask ourselves for hundreds and thousands of years, and for a couple of assignments, even in physics 1, called perhaps train of thought or something. That is, we can look at the whole world as the whole universe revolve around this special central stationary location called Earth. And we can raise a lot of questions about why are the laws of motion, laws of physics on Earth different and all involving straight line motions that are finite, as opposed to all these apparently circular, heavenly, eternal motions that we see in the sky. And eventually what we realize around the time of Galileo, or around the assignment of train of thought in physics 1, or around the advent of a telescope, eventually we start saying, oh, the question was, why does the Earth have this special property of sitting still at the center of the whole universe? The answer is, it doesn't, right? The Earth does not have a special property of sitting still at the whole center of the universe. Like, it was a good question. Why does the Earth have this special property? Because it's good to wonder, why would something have that? And the answer is right, it wouldn't. The Earth isn't special. It's just a rock flying through space like any other rock flying through space, right? And the Earth is not particularly sitting still any more than anything else in spaces, and it's not in the center any more than anything else in spaces. Well, that's also true of gravity. Earth doesn't have a special property of pulling all points of mass towards its center. Earth is composed of lots and lots of bits of mass, each of which has the same property as any and every other bit of mass. Which is that, and I'm saying this, like, you might know this, you might not, you might have sort of known this, but not thought of it this way, I don't know. I'm saying that in the same way that Galileo and Newton helped us understand that the Earth is not special, that it is in heaven as it is on Earth, so to speak, it's not special when it comes to velocity. We're now going to say it's not special when it comes to forces either. Kind of one of the big lessons of physics is that whatever motions we're seeing out in heavens are the same motions as what happened on Earth. It's all one set of laws that we are all subject to. That is kind of like the thing of physics, a thing of physics. And when it comes to gravity, what Newton ends up saying is every bit of mass, and again, you may know this or you may not, but I'm telling you so that we all know it, like, if that makes sense. Every bit of mass in the universe, call it M1, pulls on every other bit of mass, M2, like automatically exerts a force, a pull, on every other bit of mass, M2, and the exact magnitude, strength of that force, as in measured in newtons, is determined by how heavy each one of those point masses is. In fact, directly proportionally so. The heavier each one is, that's why they're in the, so I'm talking about this equation that I circled in blue here, right? This is called the Newton's universal law of gravitation. Again, maybe some of you have seen it a bunch of times before. Maybe you even saw it with me. I don't even remember, but maybe you didn't. I'm saying now, Newton's universalization of the concept of gravity, Newton's recognition that there's nothing special about the mass of Earth, that all mass does this, that any two things, just if they exist, will automatically pull on each other with some number of newtons, and those newtons will contribute to acceleration like any other newtons do. How much will any 2 points of mass pull on each other? Well, it depends on how big each one of them is. The bigger one either one is, the bigger the whole force is, and it depends on how close they are. R, so the R in the denominator, well, the R that you see anywhere here stands for displacement vector between the two of them. So the farther away they are, the less they'll pull. R is in the denominator. And in fact, in a dramatic way, R is squared in the denominator. So two objects that are twice as far as two other objects will pull on each other 1/4 as intensely, all other things being equal. Okay, that's what this is saying. It's a force of gravity. So this is kind of like right at the beginning of the year, I had to remind you or tell you about Hooke's law for a spring. Like, here's how the force of a spring works. And then we've gone to all the stuff about oscillation. Now I'm saying, okay, here's another force just to remind you or tell you there's a force of gravity. We've been dealing with gravity on the surface of Earth, but now let's deal with it with any two objects, mass 1 and mass 2, anywhere in the universe. It turns out they pull on each other this way. The closer they are, the more they pull. The farther away, the less they pull. But they pull automatically just by existing. They don't have to do anything to pull. It just happens. It's just the nature of existence is that existing as a mass is that you automatically pull on every other mass. It doesn't happen as a oh, and you'll pull in a certain number of newtons. And if you want to guarantee exactly, if you want to have the measurement correct in newtons, you take the mass of one times the mass of the other object, divide by the distance between them squared, and multiply the whole thing by a universal gravitational constant called capital G. It's not 9.8, it's capital G. I'm about to show you. And it's a number that you don't have to memorize or anything, but is simply there to ensure that our units work out to newtons. In other words, what I'm saying is, right. All right. So what I'm saying here on the next page, very sloppily, sorry. I'm positing. Again, whether you heard it before or you're hearing it now for the first time, I'm asserting, and you don't have to memorize this. It would be an equation that's on an equation sheet in an exam or whatever, but I'm saying, if you want to know how hard anything automatically pulls on anything else, any point of mass, take one mass measured in kilograms, multiply by the other mass multiplied in kilograms, divide the whole thing by the distance between them squared, and then multiply that. So like, right, if you have a point of mass, and this, I'm sorry, let me say again, what we're assuming M1 and M2 stand for two arbitrarily differently sized points of mass, like particles. Like that's what M1 and M2 are meant to stand for. We call one M1 and one M2 just as to remind ourselves that one's bigger than the other. Why? Just because it's an arbitrary case. That could be too much of a coincidence just to assume that they're both the same size. So whichever one is bigger, we call M1. Whichever one is smaller, we call M2. But I mean bigger and smaller in terms of the number of kilograms. Neither one of these, I don't mean bigger and small in terms of volume. We're talking about any dot of mass that you find anywhere, a dot, a point, a Euclidean infinitesimally small region of heavy mass. Okay, so like electron, proton, whatever. If they're separated by distance r, then you take the kilograms of one times the kilograms of the other, divide by the square of the meters between the two of them, and then you multiply that whole package by this crazy number here, this capital G, which is a universal constant. It's like Planck's constant or something. Sorry, I'll write this down. Well, I mean, it's called the universal gravitational constant. Again, I'm not saying you have to memorize it or anything, but I'm just saying here's a plug and chug procedure of how you calculate the force of gravity between any 2 points of mass. You multiply their masses together, you divide by the square of the distance between them, and then you multiply that whole thing by this number, 6.67 times 10 to the negative 11th newtons times meters squared divided by kilograms squared. Why am I telling you this? Well, I'm like, what do you need to know? What don't you need to know? You don't need to memorize that number. That number is always the same. So, eventually people remember it. I remember it because it never changes. It's always the one I plug in here. But I could look it up at any time and you can look it up and it's given to you on the exam. But the thing to understand about it, like why it's there, if it's always the same, the first thing to understand about it is it's a number. And again, this is called the universal gravitational constant. I'm not taking out my pen because I'm almost afraid to slow myself down, but you might want to write that like this number, capital G. It's not lowercase g, right? Lowercase g is like 9.8 meters per second squared. It's some kind of acceleration rate. That's not what this is. This is a constant of proportionality. This is what we just multiply our masses by, divided by our distance squared. Just if you look at it, and you're sort of getting used to this now, think of this kind of like Remember omega, when we introduced omega, we introduced it because we knew we needed radians, but we had something in seconds. So we introduced something that was in radians per second in order to cancel out the seconds. That's what's happening here. G is a number that is introduced into this equation. Specifically, I'm about to be interrupted. Here comes the interruption. 3, 2, oh, maybe not. Or maybe. Okay, well, G is specifically measured in, as you can hopefully see. Pardon me for a second. Okay, sorry. How many ADHD professors does it take to screw in a light bulb, right? Okay. I'm so, wow, I'm really so distracted. Sorry. Or I'm so distracted. G is measured in units of. Oh yeah, are you? Of course. Are you? Oh yeah. Have we? Yeah. I'm sorry. Yes, of course. Like, how are you? Yes. We'll share pills later. Okay. Of course. I mean, no. When I was young, they just called it being smart. I'm sorry, but no. But definitely, G is measured in newtons. I also didn't know it until I was an adult. Sorry, I'm talking about. Okay, what? How could you even? Okay, G is. Ooh. G is measured in newtons times meters squared divided by kilograms squared. Like, that looks like a big clunky mess, but that's deliberate. It actually is there in order to make sense, not to not make sense. It's saying that G is there to cancel out the meters squared in the denominator of GMM over R squared, and to cancel out the kilograms squared that are in the numerator, and have us just be left with newtons. Like, the whole gravitational force has to be measured in newtons. So that 6.67 number is just actually like excuse me for a second. Hello, how are you? Hi.
Can you help me find YouTube?
Yes, this is not that class, but I will tell them. Yes, I'll ask. Yes.
I just needed the stuffy.
Oh, for real? You're at
The
okay,
stuffy.
wait, okay, I'm in the middle of class. Okay, Mom's not. Wait, I can very quickly, but I do have to do this class. This is the last class.
Hi.
Hi.
Hi. I think I got it though. Thanks, Dad.
You're welcome. No problem. All right, pleasure doing business. Love you. I will see you soon. Okay. Yeah. Okay. You have one. Now I've got to teach you.
Yummy Kit Kat.
Yes. You've seen all my tricks. Okay.
Thank you.
Love you. Bye. Good to see you. Okay. Sorry. Okay. So G is there to cancel out the units of all the other stuff and leave us in newtons. It's just a big conversion factor, right? So that's why it's also not worth memorizing. We wouldn't need it at all if we didn't insist on measuring in meters, kilograms, and seconds. But also notice it's a very small number. It's 6.67 times 10 to the negative 11th, right? That means, move the decimal place over 11 places. So in general, any two random masses you ever picture, like a human body and another human body separated by 5 meters, what I'm saying is that automatically any two things, like you and your sister, or the Coke can on your desk, and like a piece of lint in the middle of somewhere, like any two things you can picture are automatically pulling on each other gravitationally. Like, it's not something that just Earth does. It's something that every single point of mass in the universe does. But if you take a typical mass and you calculate the gravitational force that it exerts on some other typical mass, like you just literally run the numbers that I'm talking about here, you plug in, which you're all capable of, you multiply a couple of kilograms by another couple of kilograms, divide by some number of meters squared, and then you multiply by this tiny number, capital G, 6.67 times 10 to the negative 11th. And so once you multiply by that tiny number, the typical gravitational attraction between any two typical objects that you could think of is a tiny force. Now, it's a force. It's there. It is one force that would contribute to acceleration. But if there's any other forces going on, like friction, gravity is a tiny force. It's easily overcome by such things as friction, as strange as that might sound. Gravity doesn't start becoming relevant until the masses start becoming really, really big, like planets and stars and moons and so forth. So gravity starts taking on these important consequences once we gather enough mass points together and make a big enough mass to actually have an effect and start pulling things toward it and start causing orbit, like planet Earth. Okay, but so the first point here is that gravity is universal. Earth is just a big example of it. Okay, and now for some, so I'm just introducing a force here. And now I'm saying, sort of strangely, sort of annoyingly, maybe sort of stressfully, maybe like right as an example coming, I'm saying, okay, there's this force called gravity. We've looked at spring forces, we've looked at other forces. Let's take this gravitational force and let's ask kind of a weird question. This question in the test, it's going to say, let's actually put ourselves, like, if this is how every little bit of mass pulls on every other bit of mass in the universe, but if it doesn't start really mattering until you gather a bunch of masses and put them together into some large thing, like a sphere that we might call like a planet, can we ask ourselves, how does gravity then manifest itself in a big, large collection of points of mass? Like what actually happens in the solid sphere of a planet? Now, again, this would be a very weird question for me suddenly to be asking right now. I'm aware of that. It'd be a very weird question, except for two things. One, the next thread of the course, we have to heavily look at forces like gravity in a big way. So this is not just like a one-off. We've examined the force of springs a lot. Now it is actually time as we move on the course to examine the force of gravity in some detail. But it's more than that. So it's partly being, transitioned in, it's being ushered in here for that reason. But the other thing is, remember, what's good or bad about this whole big harmonic oscillation topic that we're being tested on here, like the unit, the first three homeworks, whatever. It's, hopefully it's a small unit, but it's kind of deep. The kind of lesson that I'm trying to say over and over in this unit is like, once we get the mathematics of harmonic oscillation, if we really see the general relationship that captures harmonic oscillation, then we as physicists want to be prepared to recognize, to see that math in all kinds of places in nature where it's disguised. There's a lot of phenomena in nature, super important phenomena, where we don't see a metal spring, or we don't see the string of a pendulum, we don't see a physical set of objects that actually look like they're oscillating. But yet, if we know the math well enough, we know that some variable, some value is oscillating in a harmonic way, like if the math is right. And then if we know that, we know we have all these predictive powers over it. So what I'm really trying to say is, like, and you notice in the class, we started with F equals negative KX, with a mass on a spring, like going back and forth through X values. But then what I've been trying to say with the whole first problem of this test, and then when you try to see in the second problem of the test or in your lab experience, is like, whatever we were first saying about d2x over dt squared, we then started calling it z, right? Or theta, but then we started calling it z. We're trying to say that harmonic oscillation can suddenly pop up with the most unexpected hidden variables. Okay, so it's a long way of saying, trust me, this problem maybe looks hard and weird. It is, that's why we're talking about it, but it's not, but there's a reason we're doing it, because we're here to start training ourselves to see harmonic oscillation where we wouldn't expect it, okay? Or to see how forces can produce certain effects even when we don't materially see them. So you kind of have to trust and what. So I'm going to analyze gravity now. And of course, if you're with me, hopefully somewhere this is going to bring us to harmonic oscillation. Otherwise, it's totally unfair and totally a waste of your time. It does. It will. So my question here is, what if I take a big solid sphere of mass? Could I figure out what gravity is doing inside that solid sphere? Like, what's the sum of all the gravitational effects from all the points around me? Weird question, but that's what I'm about to ask. Here's how I'm going to answer it. Right. Okay. I'm going to set it up first. Okay. Here. So I'm saying, and this is, I know it's getting a little bit something. Picture a big solid sphere of total mass, capital M. Okay. I'm going to use capital V with like weird serifs on it to stand. I'm trying to read this. So at the top right, it says so this is all about problem 3 in the exam. Okay. Top right, it says let V stand for volume. I'm just introducing that notation so we can see something. So we're going to call V stand for volume. Now I'm going to introduce a lowercase Greek letter called rho. And we're going to use rho from here on in to stand for density. for your good old concept of mass per volume from chemistry. Only I'm going to, in physics, call it three-dimensional density to allow myself, because sometimes I might want to look at mass per unit area, or sometimes I will in physics, or sometimes I'll look at mass per unit length. So I'll call those like two-dimensional density and one-dimensional density. Or maybe even sometimes a little bit later in the course, I might want to look at like charge per unit area, and I would call that like two-dimensional charge density. So there's many different kinds of densities in the world. Density just means stuff per space. So here I'm going to say from here on in physics, if I ever use the lower, and you don't need to do this to solve the problem, but I'm just showing you something, but I do. I'm going to introduce the lowercase letter rho, that Greek looking thing, and it by definition, triple equal sign, it equals dm per dv. Infinitesimal amount of mass per infinitesimal amount of volume. It's the ratio of mass to volume. Like I could just say it's m over v, but I want to express here that this concept of density, I can take all the way down to the infinitesimal level. And I'm going to, so density is just defined to be ratio of mass per volume. That's what density, right? And you know that from chemistry. Now I'm saying for this, that's triple equal sign. Density triple equal sign dm v dv. Just saying density is defined to be unit of mass per unit of volume. And that definition can hold true even all the way down to the smallest level of mass, the smallest level of volume, i.e. infinitesimal. So I'm just checking the chat. Oh, cool. Okay. Now that's triple equal sign. And that's just knowledge to have for physics from now. It's just a notation thing. Rho used for density, for three-dimensional density. Now I'm saying here in this problem, double equal sign rho naught. Like I'm right here. Oops, sorry. I'm right here. I'm saying assume that rho from now on stands for density. Well, now assume double equal sign in this problem, rho equals rho naught. That's a fancy way of saying assume this density ratio is a constant, right? Remember from physics 1 or from earlier physics, like when we talk about x naught, we mean the very first value of x. Or we talk about a naught, we mean the value of a at t equals 0, the very initial value of a, right? So back in physics 1 or back earlier in this course, if you ever see someone write like a equals a naught, what does that mean? That's just shorthand for saying, oh, the value of a at any given moment we choose is the same as what it was right at the beginning. So that's a fancy but short way of saying acceleration is a constant. Like if you see a equals a naught, it means a is a constant. That's what I'm saying here. And it's an important thing that I'm saying. I'm saying we're going to assume now, just because this is what the question's asking, assume a ball that's so solid that its density is uniform throughout. It's not thicker over here and thinner over there. Like for any cubic centimeter of volume you pick, you will find a gram of mass there, or 2 grams or 3. But go over here to 2 cubic centimeters and you find twice as many grams. That's what we're saying, right? In other words, the simplest thing to picture. Uniform density throughout. I'm assuming that. A total mass, capital M, total radius given constant R, mass throughout uniformly distributed like plum pudding. Okay, that's the situation. Very strange question again. Again, this is why we're talking about it. Like I know this is like, where's this question coming from? You'll sort of see once you see the answer to it. But you do want to just like bear with me. Just picture what the question's asking. Don't worry about why. In other words, the question's asking, can you picture a solid ball of mass everywhere throughout? Can we possibly answer what would happen to us if we went somewhere in there? So now notice, capital R stands for the constant given radius of the whole situation. Lowercase r is the independent variable R. It stands for like where we're standing in this whole mess, right? Capital R is like the whole thing. Lowercase r is some random position that we're occupying somewhere, like we've tunneled underground. We're like trapped deep beneath the Earth's surface, and we're asking, what the heck is gravity doing here? That's what's going on in this question, right? We're literally, in fact, asking, what's our weight here? Like if my weight on the surface of the Earth is mg, my mass, times 9.8 meters per second squared, then where is it? What is my weight? Like somewhere, between the Earth's surface and the center. That's the question we're asking. Again, don't worry about why, because that would throw me too. Like why? But it is what we're asking. Now I'm going to try to answer it. And I'm not expecting you to just answer this randomly. Again, that's why this is a practice test, and you're going to get the same thing on the real test, blah, blah, blah. So I'm going to start answering this now. all I know is that one point of mass pulls another point of mass in a certain way according to that equation. I'm trusting that if I had any two random points of mass, like a 3 kilogram point and a 7 kilogram point, and they were located 10 meters away, I'm trusting at this point that I could plug in the numbers and get an answer in newtons, and that would be how strong the force is, and so could you. I'm assuming that we could plug, because you guys are doing much harder things than that. So we're not practicing with the gravity equation for a million little exercises. I'm saying, let's assume we're good enough to plug and chug now. We know what gravity does between two any point masses. Now this question's asking me, somehow, can I do something with that information and figure out what's going on when we put a whole bunch of points together and get a big round thing? So this is what I'm going to say. I'm going to say, let me break this into cases or simpler cases. I'm doing the same thing Newton did. I'm going to say, in order to answer this question, I'm going to consider, oh, well, sorry. So this is just a summary of what the question is. It's saying, given this solid mass sphere, where the facts that are known, what you're given are capital M, capital R, and rho. Like, again, those might as well be numbers. We're just making this problem true for all time, regardless of what the numbers are. But assume M is like a given number, like maybe it's the mass of Earth, which is 6 times 10 to the 24th kilograms. R is a given number, like the radius of Earth, like 6.4 times 10 to the 6 meters. And rho is the mass divided by the total volume of Earth, which would be like 4/3 pi r cubed. Okay. So we're trying to figure out what is the net gravitational force exerted on some particle, on some little M2, if it was trapped amidst all this M1. It's a hard question. So the way I'm going to answer it, again, from Newton, this comes, not from my, the way I'm going to answer it is I'm going to consider a shell. Okay. And again, all right, this is given. Again, what's given is the force of gravitational attraction. And I keep writing it again, whether you knew it or not, I'm saying gravity is now GMM over r squared. You do want to get used to this equation because we're going to use it a lot in the rest of the course. You don't have to memorize it, it'll be given to you, but you want to start getting used to playing with it now. One thing quickly about it, has a negative sign in it. The negative sign means attraction. That's the fastest way I could say it. Like, if you actually analyze the vectors properly, you'll see why. But the negative means attraction. It means that it means, like, for example, if the sun, if we're talking about the sun as M1 and the earth as M2, right? You picture a line, a displacement line going from the sun to the earth. If you're asking how hard in what direction what's the force exerted by the sun on the earth, you picture this displacement line called R going out from the sun to the earth. And the force that the sun exerts on the earth is directed opposite to that line, against that line, negative sign, i.e. the line that goes from the sun to the earth. What the sun does is it pulls the earth in toward the sun. Okay, so negative means pull is what I'm trying to say, just so you, and you might know that from chemistry too, but the negative means pull, attractive. And that's what one M1 will do to another M2. What we're going to picture here, in order, this is like very sloppy here, this page, but our goal, and I'm watching the time, like I know, I'm rushing a little bit, but and again, I'm going to keep saying, I know this is a hard problem. It's not that hard as long as everybody admits that it's hard and goes step by step. If I pretended that this was a joke, then it would be, right? So it's not a joke, but going step by step, I want to remind you, and it is worth it. Going step by step, I want to remind you, the question is asking what would happen if we were somewhere immersed in a solid sphere, like plum pudding. That's what the question's asking. I think that's a hard question. So the way I'm going to break it down and try to answer it is I'm first going to consider a shell. I'm about to shift now. I want to answer the hard question of what's going on gravitationally inside a solid sphere. In order to try to answer that, I'm going to consider a shell. That is, I'm going to consider a sphere of radius capital R, but I'm going to hollow out the whole center, like, it's like a grapefruit. I'm going to take out the grapefruit and just leave the skin. Imagine that for a minute, because it's going to be easier for us to do math with. So total mass M with a total radius capital R. Now, here's where we're going to have to think a little bit, like, about, this is like more Englishy than equation-y, this part right here. But I'm going to say, if I have a whole shell of mass, capital mass M1, then I can divide this thinking into two subcases, each of which is actually not that hard to analyze. Okay, if I've got a whole shell of mass, now again, the presumption is a shell of mass means a whole bunch of little mass points all arranged together in a shell. Like each one of them is exerting gravity everywhere in the universe. Each one of them is pulling anything and everything nearby, including itself, right? So I've got this whole shell of mass. If I'm somewhere outside it, this is what I mean by case Roman numeral 1, like the blue, notice the blue up here says if lowercase r is greater than capital R. That means if I'm at a position, remember lowercase r is like very independently variable displacement from center of this whole thing. If I am at some location, lowercase r, which happens to be greater than capital R, that's just a fancy mathematical way of saying I'm outside the shell. And this is case 1 that I want to look at. Like, what do I experience if I'm outside a spherical shell of mass? Okay, that's what I'm at. I'm not asking you, I'm going fast, but I'm rhetorically asking if I were outside some shell, some spherical shell of total mass m, what would be the net gravitational effect of all these little pieces like pulling on me? So I'm over here, some little particle called M2 way outside the shell. Well, I'm going to tell you what I think the result is. And if we want super, super detailed mathematical arguments, I have a link of a video that you can watch. I'm not sure that you want them or not, but here's my basic argument. If you're outside a shell, if you take it to the extreme case and picture yourself being way, way out far outside this shell, the farther you get away from a spherical shell, in other words, the farther you get from some big circle, the smaller and smaller the circle looks to you, right? Until, yeah, I totally will. Yeah, I'm sorry. I have to remember. Please remind me. But yes, I totally will share the links to what I will share a link to a video they made that further explains the thing I'm about to say. And again, I know everybody, I'm like talking fast and spazzy, and that can make things worse for people. Oh, no problem. And I don't mean to do that, but I want to assure everybody what's weird about this problem is that there's like, it's a lot. I'm saying a lot, and I know that, but each individual thing I'm saying, I'm hoping and sort of thinking that you'll see that each individual thing I say does make sense in its own right. It's just you might not have expected that I would put them all together this way. That's kind of the nature of physics. What I'm saying right now is if you're looking at a circle, you get farther and farther away from that circle. The circle looks smaller and smaller to you. Whatever effects of that circle have on you get smaller and smaller. Like if it's literally pulling you gravitationally, well, it pulls you weaker and weaker as you get farther away. But the thing is, if you're getting farther and farther away from a circle and saying that circle is looking smaller and smaller, what you're really in a way saying is that circle is looking more and more like a point. Like the farther away you get from it. In other words, the farther away you get from a circle, the fact that part of that circle is on the right of the center starts mattering less and less. Like the distance between the right side of the circle and the left side of the circle starts becoming less and less significant to you as you get farther and farther away. Eventually, and the circle was always a circle, so it was always pulling everything in the universe towards it in equal ways, and it was always pulling them toward the center of it. If you think about it, there's nowhere else it could be pulling toward. So when you get farther and farther away from a spherical shell, the whole spherical shell, as you might expect, acts more and more just like a dot located at the center of that spherical shell. In other words, we're always for a year and a half, we've all been doing something that actually makes sense, but you may or may not have thought about it. We always say Earth is pulling us toward its center, and Earth has a mass of 6 times 10 to the 24th kilograms. We sort of have casually acted that as long as we're standing on Earth, we act as though there's this super heavy, massive thing located at the center of Earth that's pulling on us. We're sort of acting like all the other pieces of Earth all add together to just make this one big effect where we're all being pulled toward the center, as though there was just a really heavy dot located at the center. That's what we act like. And it's okay. That's actually right. If you're outside a spherical, like a spherical shell is symmetric in all 3 dimensions of space, just like a dot is symmetric in all 3 dimensions of space. So if you're outside a spherical shell, it is what I'm trying to say here in brown. It's almost obvious. You might have just been doing this all along. I'm saying if you're outside a spherical shell, it's okay to think of the entire shell as just one dot located at its center of equivalent mass. Everything will be pulled toward the center of that shell by the entire mass of the whole thing, as you might expect. Okay, that's case one. So for outside a shell, and that means, by the way, for outside a shell, well, if you think about it, then that means if you put another shell inside a shell, if you make concentric shells, right, concentric shells, then if we're outside one of them, we're outside both of them. And if we're at a certain distance from the center of one, we're the same distance from the center of the other if they're concentric. So that means if you put two concentric shells together, the total effect on someone outside is just one shell plus the other shell, as though they were both, which means you can put as many shells as you want, and the effect of a whole thing, of a whole solid ball, if you're outside it, is as though it's not a ball at all. It's as though it was just a point at its center. Something, again, that you've sort of been taking for granted for a semester and a half, and I don't want to belabor, but we treat Earth, in other words, as though it was one supermassive thing located at its own center when we talk about its gravity. We don't actually care about its radius as long as we're outside that radius. That's case one. That's this. But now, if we go to case two, and I'm just going to keep, I'm going to look at it. I think I'm going to just play this. Oh yeah, okay. And I will, but please remind me if I don't remember. I'll try to pause and share the links, or I'll put them when I post this stuff. But case two now, slightly more interesting, and kind of you'll see why I'm saying all this. Well, you'll start to. Case two, we go inside the shell. Case two, same deal. Spherical shell of mass, like in other words, hollowed out ball, right? And assume it's uniformly hollowed out, like it's not hollowed out more over here than it is over there. If we're somewhere inside that shell, and now we ask, what's the net gravitational effect on us inside? It turns out the answer is zero, which is why we have to watch this carefully. In other words, every dot of mass, if you're inside a big shell, a planetary hollowed or space shuttle, whatever, there's all this mass around you. Every bit of mass is pulling, me, every bit of mass is pulling me toward the rim, toward the boundary, toward that surface area of the mass, right? Well, and so and every bit is pulling me, and they're all adding up, all these pulls, like forces obey superposition. The net force is the sum of all the forces. They're all pulling me. The question is, which force is winning and which force is losing, and which direction do I end up going in? Well, I think what everybody could see, hopefully, is if I were truly at the center of this shell, if I were at the center where lowercase r equals 0, hopefully you can see if I'm at the center, it kind of stands to reason that I'd be weightless. That the net gravitational effect on me, if I'm at the center, should and would be 0. Meaning, if I'm at the center of a shell, if I'm like right here of a shell, of a hollowed out shell, well, the top of the shell is pulling me up to it, but the bottom of the shell is pulling me toward it, and it's the same amount of mass, the same distances across from each other. And there's mass over here to the right pulling me, but then there's mass over there to the left pulling me. So they all cancel out, and I'll go nowhere. If I'm dead center of the shell, hopefully you guys can see that. I'm sort of like, if you're paying attention, right? If I'm at the center of a shell, the net gravitational force should be 0. In fact, I'm even willing to believe if I'm at the center of even solid Earth, which was the original question, if I'm at the center, I don't think there's going to be any net gravitational force at all. I don't think my G is going to be 9.8. I don't think things fall at a rate of 9.8 at the center, because they're already there. Where are they falling to, right? There's no particular direction that gravity could possibly pull. Therefore, there's no magnitude at the center. But my question here, hopefully you can see that. But my question here is, okay, but what if we're not in the center? What if we're at some arbitrary location? If we're a little mass, a little particle of mass called M2, like lowercase m2, if we're over here somewhere at a random place, then it's not so obvious to me. It's not obvious to me that everything cancels out the same way, because not everything is the same if you're at a random place. So what I want to look for, I want to analyze for a moment with you guys. And again, well, anyway, I'm going to analyze is what? Well, I'm going to assert, I'm going to tell you so that it's not confusing. I believe that even if you're at a random location, I wouldn't have expected this, but I now believe, for a reason I'm going to show you, that even if I'm at a random location, all the forces still cancel out, and I'll be weightless anywhere inside the shell. I could be right near the edge of the shell, and I'll experience a net gravitational force of 0. I'll be weightless, not if I'm outside, but if I'm inside the one and very same shell. And I want to show why. so that this page says why. I mean, okay, but I am trying, and I'm still trying to answer the whole larger question of this exam problem. The whole larger question is, and by the way, I remember when this was on an exam of mine when I was in college. Like, it wasn't fun for me either, but it's a real thing. I'm not making this up just to mess with you, but I love it now. But I'm asking here, if I'm in a solid sphere of mass somewhere, what will I experience gravitationally? And I haven't answered that yet. I'm doing all this work in order to answer that. And then when I answer it, you'll see why I asked it. But right here, I'm saying, well, if I'm going to go piece by piece, if I'm trying to build up the situation, if I just consider a shell first, not a solid sphere, but a shell, I'm arguing now that if I'm anywhere in that shell, I'll be weightless. Anywhere in that shell. And here's why. If here's a picture of a shell, right? And I'm somewhere random. So the shell is of capital given constant radius, capital blue R. That's the radius of the shell. I'm at some random location, lowercase r, like some independent variable location. I'm just standing here, this red dot. That's me, particle called M2, right? The whole shell is called M1. Like, I should make that clear too. Sorry, the whole shell is called M1. The particle, the little particle inside is called M2. So there's M1 and M2. I'm the little guy somewhere in this arbitrary place. Now, I look down below me and there's like this red chunk of mass, like that. There's this chunk of mass that's pulling me toward it, like that piece of the shell. It is pulling me toward it, I believe, by virtue of gravitation, the force that we're talking about right now, GMM over R squared. There's definitely a MM over R squared like situation going on where I'm being pulled toward that region down there. Let's be a little bit clear and careful about this now. That region I'm going to call M sub A. And not M1, not M2, I'm going to call it M sub A. It's just like the little chunk portion of the whole shell that's pulling on me. It's pulling on me with some sort of force, like MA times my mass M2 divided by R squared or something. It's pulling me toward it, as gravity always does. I want to say, well, yeah, it is. It's pulling me toward it, but there's also a chunk on the other side of me, MB. And that chunk is pulling me toward it. Now, I don't know offhand how those two forces compare, but I want to start by saying, look, for any chunk, and these are arbitrary. There's nothing special about down or up or left or right. I'm just saying, look at any random piece that's pulling you in that shell. It's going to pull you toward it. But for any little random piece you find, you can find a piece on the opposite side that's also pulling you toward it. So there's always a tug of war. And of course, the same thing's happening like left and right as well. But let's just, try to figure out what's going on. For any piece pulling me south, there's a piece pulling me north. The question is, how do those forces compare? Which one is stronger or weaker, or are they the same? If you're following me, you presumably know that what I want to try to prove is that they're the same. Or at least I want to try to argue that. And I want to do it a little bit quickly, but that's what I'm going to do. I'm going to say, well, look, each piece pulls with a force determined by GMM over R squared. Each force is directly proportional to mass, but inversely proportional to the square of distance away, right? Both, in other words, the bigger you are, the more you pull gravitationally, but the farther away you are, the weaker you pull. Both effects are true in this law right here. So I better compare like these two. I've got these two pieces. They are of differing masses, for one thing. Let me talk about their masses. Like if one is twice as massive as the other, then it's going to pull twice as hard due to that factor. Well, is one piece twice as, I don't know. Is one piece twice as big as the other? That's my question to myself. Well, let me remind myself, remember the density of this whole thing is supposed to be a constant. Like I've got this shell here. It's not supposed to be an irregular, weird, like thin over here, thick over there shell. It's one shell of one constant thickness. This whole thing is one constant ratio of mass per unit volume. Mass per unit, right? In fact, a way to put that, remember, we said, oh yeah, I've got it written here, rho equals rho naught. It's actually important. Density at any one given region is equal to density at any other region. So if you pick up cubic centimeter of volume over here and you find 1 kilogram of mass, then a cubic centimeter of volume over there, you better find also 1 kilogram of mass. That's what we're saying. So I'm saying here then, okay, the two masses might not be the same, MA and MB, but their ratio to volumes better be the same if density is constant. In other words, MA to, like so what I have right here, MA per VA, the mass per unit volume of the A chunk must be the same as the mass per unit volume of the B chunk, according to uniform density. Now I'm going to go a step further and say, well, if the mass to volume ratio has to be the same, well, or put another way, then if the masses will differ only to the extent that the volumes differ, or if the masses will differ precisely to the extent that the volumes will differ. In other words, I'm saying if one of these pieces has twice the volume of the other, then it'll have twice the mass, because that's what density means, right? Well, then and if you follow that, so in other words, for me to know how to compare these two masses, one way I could do it is compare their volumes. Well, if I'm comparing their volumes, that means the three-dimensional region of space that they occupy. Well, one of those three dimensions is called thickness, right? Like each one of these has like a width, a height, and a thickness, if you want to call them that. And the thickness better be the same for both of them. They're both cut out of the same shell. So if they're going to differ in volume, it's not going to be because of thickness. The thickness you could just call 1 meter if you like, or whatever you call it. It's the same for both. If they're going to differ in volume, it's only because one has a bigger surface area than the other. Like one, just like on Earth, like one continent is bigger than another because it's a bigger slab, not because it's thicker. Like what would that even, I mean, maybe it is, but that's not what we mean when we say, right? So since density is a constant, what I'm saying here, since density is a constant, and since this shell is uniformly thick, the two masses, and I want to compare these two. Again, I'm going down a big rabbit hole here. Like, welcome to physics, right? I've got a question. I've got to answer a sub-question to a sub-question. Just always keep your eye on the prize. My ultimate goal is what is the force, the net gravitational force exerted on some particle amidst, like, well, right now I'm asking if it's in a shell. And I'm asserting right here that if I'm going to compare the masses of these two chunks in order to compare the gravitational pull of these two chunks, what I want to realize is the masses of these two chunks will be in direct proportion to their surface areas. Like I would have said volumes because the density is constant, but volume is 3 dimensions. One of them is guaranteed to be the same here, called thickness. So the masses, so one will be twice as massive as the other, if and only if its surface area is twice as big as the other. Right? I mean, I'm saying right, but so I can go a step further now. Surface area of a sphere. If I am, I would ask all you guys now, but I'm not. But the next question is, what's the surface area of a sphere? The surface area of a sphere. Am I supposed to remember this now for physics? Oh my God. All right, sphere. Well, so it's circular, so it's going to involve some freaking pi, right? It's like a sphere, it's like a circle. So pi is going to be involved. Is it like pi? Okay, surface area, is it like pi r cubed? Is it like 4/3 pi r cubed? Well, close, good thought, but no. R cubed would mean 3 dimensions of R, 3 like length times width. That would be for volume. If you're remembering something about 4/3 pi r cubed, that's the volume of a sphere. We want the surface area of a sphere. The surface area of a sphere is area, not R cubed, but R squared. And sure, there's a pi involved because there's circles involved. The only question is, what's the coefficient? Is it 4/3 pi r squared? Or is it just pi r squared? Or is that the area of the circle? Oh, as a matter of fact, I'm just telling you, the surface area of a sphere is, you may or may not recall, 4 pi r squared. Am I asking you to memorize? Well, it is. The surface area of a sphere is 4 pi r squared. You might recall that the volume of a sphere is 4/3 pi r cubed. And it might occur to you, oh, that's kind of weird. Like 4/3 pi r cubed. Are you saying like if I take that 3 and I bring it down, like I multiply it by 4/3, so I get 4, and I take that, that's almost like I took a derivative of 4/3 pi r cubed to get 4 pi r squared. That's weird. Is that what Yaverbaum's saying? Is that relevant to this? I don't know. I'll say this. It might be a coincidence, but if you think of the area of a circle, which is pi r squared, then you think of doing the same thing, like take that exponent and bring it down, like make it 2 pi r, you have the circumference of a circle. Is that a coincidence? No, it's not. Do you have to totally understand that? No. But I'm saying the surface area of a sphere, oh yes, it's the derivative of the volume of a sphere. And this will all become clear after the midterm and so forth. All you got to know right now is, I'm just trying to be, I don't know what, but the surface of a, this is the opposite of ADHD, right? This is the part you could call intelligent. I don't know. But the surface of a sphere is 4 pi r squared, whether you see why it might be, or you just memorize it, or but it definitely had to be a squared because we're talking about area. There definitely had to be a pi involved. And the only question really is, how did I get the number 4? And I'm actually telling you, I got it by differentiating 4/3 pi r cubed. But anyway, this is the surface area of a sphere. Why am I saying all this? Because, oh, whoa, that means if I go back to my picture, I'll try to say this as clearly as I can, but look, what we're saying is the mass of each chunk is directly proportional to the surface area of each chunk. The surface area of each chunk is directly proportional to pi r squared, to r squared, to the distance squared. So MB, let's say that MB, so I probably should put this in mathematical notation, not English, but what I'm trying to say is what I'm arguing is, given the way spheres work, if I take a chunk over here that's twice as far away from M2 as the chunk down here, if MB is twice as far away as MA is from M2, then actually, given that the surface area of a sphere is directly proportional to r squared, then that means that the one that's twice as far away, if r is twice as big, the surface area will be 4 times as large, like r squared. And therefore, since density is uniform, the mass of MB will be 4 times as large as the mass of MA. If MB is twice as far away, its mass will be 4 times as great as that of MA. But that's really interesting because if you see where I'm going with this, the very expression of gravity says that that all other things being equal, if you're twice as far away from the sun as you were 5 minutes ago, then you'll be pulled by the sun 1/4 as strongly as you were when you, right? If you get twice as far away, the r is squared in the denominator. Things that are twice as far away get pulled 1/4 as intensely, as strongly. So what I'm arguing here, hopefully you see, I'm saying, oh, in this particularly weird arrangement that we're looking at, the object that's twice as far away would be pulling 1/4 as weakly according to gravity, but it's also 1/4 as massive. So the object that's twice as far away would be pulling 1/4 as weakly according to gravity, but it's also 4 times as massive. Therefore, it's pulling. I'm saying it. An object that's twice as far away would be pulling 4 times as weakly according to the force of gravity. But in this case, if it's twice as far away, that also makes it 4 times as more massive. So the two effects completely mitigate each other is what I'm trying to argue, as you might have already seen. And I'm saying then that inside a shell, for any one piece of the shell down here that's pulling you in some direction, you could find a piece on the opposite side that is pulling you exactly as hard in the opposite direction, because it's r squared more mass pulling you, but pulling you more weakly by a factor of r squared. We're saying the r squareds cancel out and lead to this effect of all the interior of a shell being weightless. That's what I'm arguing. Why that? I'm going to have to keep going. I know it's like we've got 7 minutes. What I'm arguing right now, to try to put this, and again, this is, if you've been with me, the hardest part is knowing why you would care, really. But if you're still with me so far, we're over the hump of the problem. The rest will seem more like science to you or something. That right now I'm arguing, if I want to know what's going on inside plum pudding at some variable displacement from the center of some solid sphere, what I'm arguing now that I think I know now going into that problem is, I think I can believe that if I'm anywhere outside a sphere or a spherical shell, I'll experience just regular gravity as though from a point at the center. And if I'm anywhere inside a shell, I'll experience a net gravitational effect of nothing, of zero, of full cancellation. I'm now going to put those two facts together to finish this problem, to answer this problem, and to hopefully show you why it's a problem in the first place. I'm now saying, yeah, all right, so I just read this. And you can I'm saying then, if we go into a variable location R somewhere into the interior of a solid now, which is the question. I believe I know something about being outside shells. I think I know something about being inside shells. I'm now about to address what happens in a solid, which is the purpose of this question. If I go inside a solid, anywhere I am where such that lowercase r is less than capital R, I'm somewhere in this planet seed, this solid's interior, where the density is a constant. And, sorry. What I want to argue, and you really, this is okay, I say everything up until now is hard. It's hard to listen to everything up until now. Here's the part I'm about to say that's the key to the whole thing. If you're still with me, the key to understand now is I'm saying, if we know what's happening when we're inside a shell, and if we know what's happening for outside a ball, to be inside a ball really is to be both at the same time. If we're inside a ball, we're standing in between an outer shell and an inner smaller ball. Really important. It's like so dumb, but really important. If I'm standing somewhere inside, if I'm at this point right here at lowercase r, if you think about it, there's all this mass above my head. It's like there's this big shell of mass all above my head, right? And then below my feet, there's this smaller like sub-planet, which I'm going to call the enclosed planet, the blue planet. If I'm inside of fully immersed in mass everywhere, there's all this mass above my head, all pulling me. And then there's all this mass below my feet, all pulling me. Well, I want to say now, we're just in a sandwich between the two cases that we just argued. We are inside a shell, outside a ball. So everything in the shell will cancel out. So the total net of gravitational effect of the whole thing is just that, the sum of all the gravitational effects. Well, all the gravitational effects from the shell will all cancel out to zero. We just argued that. In other words, everything above my head doesn't matter. That won't affect me at all. Everything below my feet will pull me as though I'm just standing on a planet of that size. If I'm immersed in the earth, it's as though I'm standing on a smaller enclosed planet that I'm literally going to call the enclosed mass, the blue thing. And that's all that's pulling on me. And it's all pulling on me as though we're all located at the center, because that's like a regular planet now. So if I just knew that mass, I would know the answer to this whole question. And that's what I'm going to do right now with the 3 minutes. So I need this I'm saying the total gravitational effect of something inside a solid is ultimately the total gravitational effect only of the enclosed solid, the solid material that is below the radius at which you're located. That's what I'm saying. So all we need to know is what that mass is expressed in terms of given known constants, and we're there. So our job here, and again, I'm going a little bit fast, but our job is we're literally going to just plug in. We're going to plug in GMM over R squared and solve, but the big M that we're plugging in here that we want is the enclosed M. Like how much mass is at that blue line as a function of known or given constants. In order to do this, we invoke uniform density. The mass per unit volume is a constant throughout. So meaning, if you look right at the bottom of the page here, or in fact, I'll just go straight to the next page. But trust me, if you go to this page, I'm saying for like M1 over V1 equals M2 over V2, any mass to volume ratio, it has to be the same. So the total enclosed mass per the total enclosed volume has to equal all of the mass divided by all the volume there. So I'm here now. Therefore, the enclosed mass, I'm just multiplying both sides by volume enclosed. The enclosed mass that I'm looking for, so I can plug in to GMM over R squared, the total amount of mass just under my feet here, what it is the total amount of mass divided by total volume multiplied by enclosed volume. Volume of what? Volume of a sphere. A sphere volume is 4/3 pi r cubed. So the total volume of the whole thing is 4/3 pi capital R cubed. And the volume of where I'm standing is lowercase r cubed. So I'm plugging in. We're just about, what happened? Okay, we're almost done. I know we're almost done. And again, if you have to go right now, just obviously I'll publish all these notes and publicize, but if you could bear with me for like 2 minutes to get the end, that would be great. But if you have to go, I totally understand. And I have to go so what I'm saying ultimately through all of this, and we really are nearing I'm saying that the total enclosed mass, the only mass that matters, is some fraction of the entire mass. What fraction? Well, a fraction determined by where you're standing. Like basically, in short, if you're standing halfway out, then you're enclosing 1/8 of the volume. That's what this says, because volume is a function of r cubed, because it's three-dimensional volume. So if you walk out halfway to the edge of this whole ball, you're standing on an inner planet that in effect has a volume of 1/8 of the original, and therefore a mass of 1/8 of the original. So we plug that in. So we found that M, again, we're just about there. We found that M enclosed equals total M times this ratio of cubes, lowercase r cubed divided by, and it's just a ratio. The units will cancel, and so it's just some fraction of the whole original. So we plug that in to the gravity equation. We plug that in, m1 r cubed over, and we notice that the lowercase r's cancel out. And here we're just about done. And what we get here is, so this is the answer to part A. This is literally the answer. And then I'm going to say quickly what it does for us in the answer to part B and why we're talking about all this and stuff. The answer we get for the gravity inside a solid, like gravity outside is blah, blah, blah over lowercase r squared. This says that gravity inside is directly proportional to r. Gravity inside is F equals negative blah, 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 r, not r squared in the denominator, but r. We did all this work to notice that if we were to, like, this is literally saying, go to the center of the earth, your gravity is nothing. You're weightless. Your 9.8 number is 0. Go out halfway to the edge of the earth, you're up to 4.9 now. That's what this is saying. Your weight is like half of what it normally is. If you out to halfway, like literally we're saying it's linear as a function of r, of how far out you are. But with a negative sign, meaning that if you go out from the center of the earth, you're always pulled back toward the center. Oh, negative sign. Oh, linear. Oh, I'm saying, oh, look, this weird linear force, GMM, all these constant times R equals MA if you're in free fall. And A is a second derivative of position with respect to time. I'm saying here very quickly now, but that was all the hard part. I'm saying we just did all that work to show that if you carve out a tunnel in this through Earth, through the diameter, you carve out a tunnel and you drop a rock in that tunnel with nothing in the tunnel, just gravity. Gravity will act on that rock the same way a spring force acts on a spring. It will pull the rock toward the center, and the rock will fall toward the center at a higher and higher rate of velocity, but at lower and lower accelerations, right? Because it has the most acceleration when it's on the outside, just like a spring, most potential energy. It'll be falling in. By the time it gets to the center, it's going super high velocity, super low zero acceleration. Every single moment, it's changing its velocity, it's changing its acceleration. How could we pop? And I know it's 4:22, and I'm very sorry, and you can go anytime, and I'm just about done. But the point is this: what we just went through all this work is to show that gravity ends up acting like a linear restoring force inside the Earth. We have that quality of d2r over d, like the variable now is r, but so what? Second derivative of r with respect to time apparently equals negative times some constant times r itself. So we have a harmonic oscillator due to gravity, meaning literally, we've got something that's going to oscillate back. If you drop a rock in this tunnel, it's going to gain speed, then lose speed all to the other side, and then come back, go back and forth, and it's going to go it's going to oscillate at an angular frequency, which is the square root of this constant inside the differential equation. Hello. So it's got an angular frequency of the square root of that constant, which means just divide that by 2. I'm speaking fast, but it's all in the solutions anyway. But the key insight is we did all that work to see that, oh my God, even though there's no metal, there's no spring, there's no pendulum, there's just gravity. In this case of being inside the Earth, gravity acts like, it does produce a harmonic oscillation of a period that is calculable. And if you actually plug in the actual numbers here, I'm saying very fast, but again, this will all be written, you can have all this, of course. If you plug in realistic numbers like the mass of Earth, the radius of Earth, the universal gravitational constant, and try to calculate what the period of this oscillator through the whole Earth is, you will find, and check this yourself and check it. But if you plug in the numbers properly, do scientific notation properly on your calculator, you'll get that to go all the way there and back one cycle. And we're just about done. And thank you for your 5 minutes. And I owe you 5 minutes back of your life. Of course, we started 5 minutes late. That's why this happened. I'm sorry. But you will find that the period of this oscillator, like 2 pi over omega, the amount of time it takes to go all the way across the Earth and back is 84 minutes, which means to go across the tunnel once would be 42 minutes. That's actually the answer to part B of the exam. How long does it take to get to the other side? 42 minutes. And here is the kicker. I'm just going to tell you because it's just too interesting not to know, so you can understand part C of the exam. I probably won't put part C on your exam because I'm saying this so quickly now. But the kicker is, if you get harmonic oscillation and you get that we just proved that gravity can be a harmonic oscillator, and you get that that harmonic oscillator is an oscillation which is constant in time, irrespective of space, right? A harmonic oscillator has a frequency that's independent of amplitude. Then I'm going to tell you right now, the most mind-blowing thing of all is that even if it's unrealistic to cut a tunnel all the way through the center of the earth and go to the other side, like who's going to actually do that realistically? Nobody. It turns out if you cut a tunnel anywhere in the earth, from Brooklyn to London, or Brooklyn to Tokyo, or Brooklyn or Manhattan to Johannesburg, or Manhattan to Queens, any tunnel from one edge of the earth, and I'm sorry to keep this long, but this is so worth saying to me, you carve a tunnel from one edge of the earth to another piece of the earth's surface, a tunnel, a cord, it doesn't have to be a diameter, any random cord that goes from one place to another, what you'll find is you'll find that you have there, even in a short squat tunnel, a harmonic oscillator of different amplitude, different size, much shorter than a diameter tunnel, but the same angular frequency. You'll find the same gravitational oscillator in any tunnel you carve of any shape or size, or of any size through the earth. And what you know about oscillators is amplitude does not determine frequency. So it turns out any tunnel from any point in the earth to another, if you really carved it out, got rid of the friction and just had gravity there, the trip that a rock would take from one edge of any tunnel to any other, Brooklyn to London or Brooklyn to Queens, it will take that rock 42 minutes to fall to the other side. 42, always, like literal number. Because if it's a really big tunnel, the rock will have a huge amount of potential energy at the beginning and go really fast on average through the tunnel, like a harmonic oscillator. If it's really short amplitude, then there'll be very little potential energy, very little kinetic energy, and the rock will dribble very slowly. No matter how long that tunnel is through the center of the earth or not, it'll always take 42 minutes to get to the other side, because that's the nature of harmonic oscillation. But that is a lot, and your version on the actual exam will be trimmed down from this, believe me. But you still do want to know this. I'll publish the notes, and I'm sorry to keep you so long, and that's it. That's it. Sorry. Goodbye. You've been very patient. So I'm good if you're good. I'll wait for a second to see if I get killed. But I'm good if you're good. And I could turn back the pages or whatever if you want. Oh, goodbye. Thank you. Thank you. So, thank you. And I'll publish a bunch of things. I mean, thank you, guys. I appreciate it.
Thank you, Professor. Take care.
Thank you.
Thank you. See you Monday.
Thank you. Yes, see you Monday. And I'll put the link in, and I'll share the link. Cool. Cool. Thank you. Awesome. Thank you. Okay. You good, Elia? Are you copying anything now? Or should I go?